regular Friday seminar series on this day. Today, it's going to be a little different from the traditional sort of theme of your expertise in that electrical engineering. Today, our speaker is Kazi Faraz. She received her BS degree in Industrial and Production Engineering from Bangladesh University of Engineering and Technology in 2012. In short, it's called BUET. And she is currently a PhD candidate at Industrial and the System Engineering Department here. And her research interests includes neuroergonomics, brain-computer interface, machine learning, and human decision making. Just to give you a brief shot for what she's been working on and I've been working on together is my lab focuses on three things. The first one is the human decision making judgment. The second one is the brain-computer interface. And the third one is the machine learning, probably you guys are aware. And she's very much enthusiastic for all these things, and she wants to combine everything for her work and as well as for her dissertation research, as well as Dr. Homayfar's research collaboration there. So um, I've been working with her, and then we've been making a lot of progress, and hope to make a good contributions in this BCI area. And so, without further ado, Kazi, it's all yours.
Thank you, Dr. Song, and thank you, Dr. Humar, for giving me the platform. Good afternoon, everybody. So today's presentation topic is under neuroergonomics domain. That is, our presentation topic's name is investigation of neural correspondence associated with brain binary decision making at go no go task. So this is the overview of my presentation. I will go through introduction, literature review, research objectives, experimental design, methodology, analysis, and result. I'll give a brief introduction of neuroergonomics first. So this is our domain, as Dr. Sopins mentioned already. It's a broader domain of the research. So what is neuroergonomics? Neuroergonomics is the study of the human brain in relation to performance at work and everyday settings. It's the human factor we know that the ergonomics works with the human engagement with the work. But when it comes from the neural or brain perspective, it becomes neuroergonomics. So at the left side of the picture, you can see that our brain is associated with lots of tasks like planning, motivation, movement, sensory, and our brain is divided in lots of small and intricate segments, and those segments are found to be associated with different kinds of tasks. So if we want to kind of go to the basic or kind of try to simplify all those tasks, we can divide our brain into 4 lobes: frontal, parietal, temporal, and occipital lobes. And studies has found their association with different kind of mental tasks. Like here in the left side of the picture, you can see the frontal lobe is associated with conscious decisions. Parietal lobe is associated with information processing and motor movement like skeletal muscles, limbs, head, and eye movement. Occipital lobe is associated with visual processing, and temporal lobe is associated with memories, language, and emotion. Why not to know about neuroergonomics? So neuroergonomics is a broader domain under which we can discuss lots of things like brain-computer interface, human automation interaction, automated vehicle, and lots of things. Like for automated vehicle, if we want to want to use it for disabled people. We would like to bypass the motor function. So, and when it comes to human automation interaction, when we talk about automation, we don't who are working with the technological side, they do not think of human, and that's not that task too. But when we who work with neuroergonomics or ergonomics, we include the human and we try to understand how the automation, how the human is interacting with automation, like what kind of tasks will affect the human, how the decision making, the trust, their emotion, those kind of things, what kind of visualization will help them, etc. And if we talk about brain-computer interface, it is about building a bridge between human cognitive activity and computerized system, bypassing motor function. Lots of practical uses we can see as exoskeleton, robotic arms, scalar matrix, and so on and so forth. So we can look at a short video. It is not in the presentation I shared with you because the file size was too large. But you can see here, it's a scalar matrix, and this person is trying to spell a word with her brain signal. So it's a matrix of letters, and she's focusing on a single letter. And when the letter row or column of the letter flashes, the brain produces a special signal, and that's how the computer detects it, and the system detects it, and it can spell it accordingly. So she is trying to spell it try EEG. So this is how you can see she has already spelled, she has already been able to type 4 letters of DRYE, D-R-Y-E, and this is done by flashing the rows and columns of the matrix. And if you can look at the picture at the right side, you can see the rough schematic of how it works. So the signal is acquired from human brain, and then the feature extraction, pattern recognition, and all those kind of signal processing is done. Then the signal is sent to the computer or the system, and then it works to control the machine, we can say in general. And here in the picture, a robotic arm is shown. So let's look at a little bit more about brain-computer interface. As we said, that it's a bridge between human brain activity and computerized system. So let's have look some of the examples BCI has been done to help the people who cannot use the motor function. A web browser and a multimedia user interface have been adapted from BCI control for the aid of severely motor impaired people using dynamic P300 scalar matrix. We have already seen the, how the P300 scalar matrix works. An internet browser that has been developed through the real-time classification of P300 ERP to aid severely paralyzed persons. And we have also seen the other. I have also discussed about other use of the BCI like robotic arm and exoskeleton. But in spite of all those advancement of BCI technology, it still has the lots to do. Like some feature of current technologies can cause fatigue to the users and not convenient to all kind of users, especially who are physically challenged. And sometimes when the BCI is used to support the patients complains about frustration, fatigue, stress, and that's where we need to we feel the need to explore the neuroergonomics more when we will understand the human brain more and their specific functions. The technology and the devices will be able to much easier to use, and we will be able to simplify them. So to know the brain function and to know brain function and to know the neural activity of human brain, there are lots of techniques available and being used. Some of them are really complicated, like surgery and invasive techniques. But the more common techniques is brain imaging techniques. That's also used in medicine domain and medical domain and the technology domain. So I'll discuss some brain imaging techniques here. So brain imaging technique is various that kind of techniques for either directly or indirectly image the structure, function, or pharmacology of the nervous system. At the right side of the picture, we can see several brain imaging techniques is mentioned, like EEG, MEG, fNIRS, PET, fMRI. And if we look at the axes, it is like some of the techniques has better spatial resolution than others. Some has better temporal resolution. Some is great with spatial and temporal resolution, but has difficulty to use. So I will briefly discuss about their pros and cons here. So first, I'll go with electroencephalography. It's a non-invasive technique to record electrical activity generated by brain. Though I'm saying it here non-invasive, but it can be invasive too. But for lab purpose and to understand the neural action, the non-invasive EEG is more used. They simply record the electrical data from sensors placed at the scalp surface. This technique is highly used in neuroimaging researches due to a high temporal resolution. It's inexpensive. It is easier to operate and handle. It's easy to move or relocate. And one of the techniques or methods used in electroencephalography is ERP, or event-related potentials. Those are cerebral generated electrical voltages recorded on the scalp in response to specific stimuli or responses. Like when we record the EEG on the basis of some events, and we get some potentials, then the study is like ERP study, we call that. Another technique is magnetoencephalography, records the magnetic fields generated by neural activity. It has great time resolution, and it can capture the deeper neural activity much better than EEG. But it is large, stationary, expensive, and normally it requires heavy technical knowledge and maintenance and training resources. That's why it's not that much friendly for normal lab researchers. Another one is positron emission tomography. It's a nuclear imaging technique based on gamma radiation caused by decaying radionuclides, which are inserted into the body of the respondent. Can monitor metabolic activity like glucose metabolism of neurons during cognitive activity. Much more robust towards motion artifacts, but they are lacking the high time resolution of EEG recording. Another one is functional magnetic resonance imaging. It is a technique that is widely used in lab purposes and neuroergonomic researches. It measures the changes in blood flow, which is associated with changes in neural activity. Increased neural firing requires oxygen, which is delivered by blood. The change in this magnetic property measured as a distortion of magnetic field. It has excellent spatial resolution, but it doesn't give the good time resolution of EEG. Another one is functional near-infrared spectroscopy. It is a lab-friendly tool too. It measures brain activity by using near-infrared light to estimate cortical hemodynamic activity, which occur in response to neural activity. It's non-invasive, safe, portable, low cost, but it doesn't have good time resolution as EEG or good spatial resolution as fMRI. So let's take a better look at electroencephalography, because that is the tool we are going to use and we have used. So as I have mentioned, it uses an array of electrodes all over electrodes on the scalp and collects the electric signal. So in the central picture, you can see a person is looking at a computer, and he has lots of electrodes attached to his scalp. So this electrode system normally is used in electroencephalography is 10-20 electrode system. So the 10-20 electrode system divides the scalp surface into in some regions, and denotes those electrode names as some combination of letter and number. So we can see here we use letter F, T, C, P, and O. We already see that our brain surface can be divided into 4 lobes. So these letters F, T, O, P, those are for frontal, temporal, occipital, parietal lobes. And the C is for central region, though there is something physical called central lobe, but for understanding of the region, the C is denoted for central, and the letters are for the odd numbers are for the left side brain, and the even numbers are for the right side brain. So once we collect the signals through these electrodes, we get this kind of graphs, and then we analyze them from different perspectives, like time domain, frequency domain, time frequency domain, etc. So when in EEG study, P300 signal is P300 signal or P300 probably is very highly discussed or studied area. So P300 is a form of visual evoked potential. So when somebody uses EEG related to visual responses, P300 gives lots of information. The P300 comes from the name. The P is from the positive potential, and the 300 denotes that there will be a peak, or there will be some potential noticeable at the 300 order. Like it can be 300, it can be 350 millisecond order after the event. So it's kind of the ERP. So different types of paradigms can be used in P300. That's the single stimulus, that can be oddball paradigm. So in oddball single stimulus, it just measures like one signal is given, and once a signal is shown to the participant, and then the ERP is measured, and it is seen the what is the characteristic of P300 signal. That is, after 300 millisecond of the signal, if the signal has bearing any kind of special characteristics like amplitude, latency, or if we look from the frequency range, we can also analyze that. So when we try to analyze from the frequency range, the the frequency range emitted by human brain can be divided into five kind of frequency ranges: delta, theta, alpha, beta, gamma. So the delta is 1 to 4 hertz. It's associated with sleep. Theta is 4 to 8 hertz. It's associated with mental load or working memory. Alpha is associated with alpha is 8 to 12 hertz. That's associated with relaxed state. Beta is associated with busy thinking. It's between 13 to 25 hertz. Gamma is greater than 25 hertz, and it's associated with attentional process. And this P300 is the signal, is the technique which is used, what we have seen as scalar matrix. So it's, in this picture, you can see a very traditional scalar matrix, but it can be modified into different kind of matrices as per needed. So with all these techniques, what we are going to do, as we said in the topic, we want to focus on decision making. So I will give a brief introduction of decision making to let us revise the idea of decision making, like how complex it can be. Decision making is a complex process and cannot be described in a simple form anyhow. Even a single mental task like moving a finger needs decision making. Maybe that's subconscious, but it needs 3 distinct steps: temporal and functional aspects. The assessment of options and formation of preferences, the selection and execution of an action, the experience or evaluation of an outcome. So there is some studies found with the decision making, that what kind of process goes with decision making. So some studies found that 2 parallel processes may come with conflicting outcomes while doing the decision making. One is evolutionary, older, faster, kind of automatic, and that's not accessible to conscious awareness and control. Most of the time, we cannot say why we made this decision because of this kind of process. And other process is based on rules and algorithms and formal logic, and it's slower. So we can kind of think of intuitive and analytic thing in this purpose. Neuroimaging studies in different brain region patients and in their decision-making paradigms. Several investigators found that that the decision-making process can be associated with reward, punishment, positive and negative moods. So we can say that decision making is affected by this reward, punishment, and positive negative moods affected. And some studies found, like an fMRI study, found that in decision making in adults there is a high individual differences. So here we can see a picture. There's decision making connected to different kind of process. So in studies, they found that there's 37 kinds of mental process that can be associated with decision making. But even we try to simplify them, we get this picture that says that decision making process can be compared to a problem solving process, and it can be connected to comprehension process, qualification process, quantification process, memorization, representation, and search process. So whenever we do a decision making, regardless of how complicated is this, they're associated with this kind of other processes. So from the previous slide, we see that there is no such thing as simple decision making. To understand the basic of binary decision making, we aim to explore the neural phenomena associated with decision making that might require less cognitive tasks. We want to minimize other effects like emotion or mood or other effect, reward punishment effects in our study as much as possible. That is why we chose go no go task for this experiment. So traditionally, the go no go task experiments involve simple two choice tasks in which participants request to respond to stimuli, to push a button for go, or usually restrict the movement for no go. So so neural correlates of go no go task can be interpreted or indicated associated with two choice, or if we do further study in multiple choice alternative tasks. So findings regarding these neural correlates of binary tasks can be incorporated into more complex practical use. The small unit of binary task can be incorporated in different BCI technology that includes binary cognitive tasks. This finding can be applied in transportation system for support of vulnerable road users to respond to the traffic signal, or in any automobile where direct physical intervention is not possible. The binary decision signal can be used for emergency management where physical intervention is crucial. So in few words, we can say that when we cannot intervene physically, we want to use our brains to control the system, and that's why we go for a unit task, and we aim to integrate this simple task into a more complex design. So literature review of go-no-go task shows us that the go-no-go task experiments are mostly incorporated in studies regarding response inhibition or performance. They measure the error and response times to evaluate the performance in different situations. So in studies, it has found a slow negative potential elicited with which indicates response preparation. We can interpret that decision to response. A study of ERP components and behavior in auditory equiprobable go-no-go tasks measures response inhibition in young adults. And another study shows go-no-go task go-no-go task for to understand response inhibition in different kind of social drinkers, and they also try to measure the inhibition effect. Posterior brain ERP patterns associated with go-no-go tasks in children has also studied to understand the difference between different age group of children. And also other kind of studies have been done in young children, like to measure the response monitoring and behavioral attitude, go-no-go task. So in our knowledge, we can see that the go-no-go task mostly aims to measure performance, observing error rate and response time for different participants, like children, social drinkers, or with some kind of psychological condition like anxiety. But so far, as per our knowledge, we have found no study that has been conducted to explore the neural correspondence of go-no-go tasks to investigate decision-making cognitive tasks. So in our study, we want to use this go-no-go task design for our binary decision problem or our binary decision research area, so that we can identify the brain region associated with the cognitive task. And we also want to observe the characteristics of the neural signal. We want to observe the effect of different kind of stimuli like visual, auditory, and stimuli. And we also want to see if different kind of presentation has any effect in those kind of binary decision-making thing. So even with this simple go, no-go task, we can say there might be lots of influences of stimuli. So we want to explore that area. So when we decide to do go task study for our binary decision problem, our main task was to design a proper experiment, because we don't want to use simply the performance or error rate. We want to understand the brain function while making the decision, while doing the decision making task. So for our pilot study, we designed 5 experiments, and we use different kind of stimuli and different kind of presentation order to find out which will give us better understanding for the brain function. So for the first experimental design, we use green dot and red dot. We actually here wanted to mimic the practical scenario of traffic signal. When you see the green signal, you go. When you see the red signal, you do not go. So in our experiment, green dot is shown consecutively 10 times at first for 5 seconds each. Like one green dot is shown for 5 seconds, then 1 second of blank, then again 5 seconds of green dot. So that's how that's the way we show 10 green signals for go. Then simultaneously 10 signals for no go with red dots. Then in the same run, 20 go signals. Then in the same run, 20 red signals. So while seeing the go signals or the no go signals, participant press the B button for both the stimuli. So here we use the same response because we wanted to see if there is no motor distinction, like there is no difference in motor activity. Is there any difference between just the cognitive task, like when the human is thinking go or no go, if there is any difference? Experimental design 2 is almost same as design 1, but we use 2 different stimuli. We use different stimuli, as we see as pedestrian in traffic signal system. Go for a white walking figure and no go for a orange palm. So we changed the presentation time here from before we used 1 minute for 10 signals, but here we will go for 2 minutes. That means 20 signals of go, then 20 signals of no go, then 30 signals of go, then 30 signals of no go. And here too, both go and no, for go and no signal, participant will press the B button. So here we change the timing because we wanted to know if using the timing will give us better understanding, so that we can use the better design for further experiment. In experimental design 3, we used American Sign Language for go and no go. It's almost same as the experimental design, but here we decided the participant was to press the B button for go, and for go no go signal they will do nothing as traditional go no go task. So for experimental design 4, we have gone for generic thumbs up and down. If you see the thumbs up, you're okay to go. If you see the thumbs down, if you do not go. So as like design 3, design 3, you press the B button while saying go, and you do not do anything for no go. And experimental design 5 is a little bit different than the last 4. We use here equiparable presentation of all go no go stimuli mixed. All the 4 go signals of previously discussed, and all the 4 no go signals appears randomly 16 times. And the participants are to press B button for go signal and N button for no go signal. So while doing the experiment, the difference we have discovered that the sometimes for the first four designs, the participants were they are saying that they are getting carried away, but with experiment design 5, they were more alert and they were having a little bit of more cognitive tasks, like they had to memorize which one is go and which one is no go, and they had to be alert, like they don't know which one is going to appear. So with this experiment, collect signals, we use 12 channels. Those are F7, F3, FC, F4, F8, CZ, P3, PZ, P4, O1, OZ, and O2 to observe the signal characteristics. You can see here as the green highlighted ones in this electrode system picture. It chooses 12 channels from based on previous studies and literature review. We use G recorder to collect, amplify, and record the signals. Then we average the data over all the go triggers and all the no go triggers separately. Like for experiment 1, we averaged over 30 go markers, and again we averaged it over 30 no go markers. And the average we did is over 5 seconds around the trigger. Like we considered the trigger as zero time, and we took the time from -1 second to +4 seconds of the trigger. So here is kind of, you can visualize how we presented in the experiment 1. So you can see the blue line and red line. So there are 10 blue lines consecutively, then 10 red lines consecutively, then 20 go, and then 20 no go, that means red. So we averaged over those triggers, and we can see that the pale blue line is for our trigger over which we averaged. And here we can see 4 pictures. Those are for go, no go, average signal for participant 1 and participant 2. So you can see they are not very same, and there are lots of difference. Even if we see overall, you can see that there is a significant difference in participant 1 and participant 2. So with participant 2, we see the voltage range is much wider than the participant 1. And with participant 1, we can see there is if you can see my cursor, there is a peak around 300 millisecond. As we discussed, there's something called P300 phenomena. So we can see here. We still don't know if it is the ERP and P300 phenomena, but we are guessing it is associated with the P300 phenomena. So with both go and no go, we can see this kind of thing in participant 1, but participant 2, we do not see any such kind of thing. So as we see in literature review, there is individual effect in adult decision making. Maybe that is reflecting here. And we also see that the participant 1 average data, we see that there is there is there is something special in potential at F7 electrode, but there is not for no-go signals in participant 1, but for go signal there is no such thing. And for participant 2, F4 electrode is working rather than other electrodes, and so we can see that the distinction of go and no go is not very clear in participant 2, but overall we can see that the parietal region, the P4 electrode is stimulated in all of these pictures, though their voltage range is different. So in map, if we look at that, it kind of reflects the same thing for go, no go in participant 1 and 2. As there was some significance in participant 1 in with 300 milliseconds. So we just captured here if at that range we can see something. This map kind of reflects with our previous findings. So if we summarize our observation, we can see that right side of the parietal region has strong association with both go, no go tasks for both of the participants. The left side of the frontal region has association with no go signal of participant 1, while S4, that means the right side of the frontal region has association with both kind of stimuli for participant 2. There is a clear P300-like phenomena observed in participant 1, while that is not visible for participant 2. There is also a small but sharp peak observed just before the trigger. Go back. We can see here for participant 1, there is a small sharp peak. So for participant 1, which we assume that might be associated with the stimuli presentation, like when the stimuli appears in front of the participant. But that is not observed in participant 2. So from this experiment, we can come up to some hypotheses. Those are individual effects have significant association with neural function while decision making. As we have seen, there are different observation in two participants. Frontal zone and parietal zone is active while doing go/no-go tasks. The signal from frontal zone might be able for classification for further practical use. Only in one participant, we have seen that the F7, that the left side of frontal region is differently active from that of go signal. So maybe when we digitize the signal, we will be able to classify them if we find the same phenomena in more participants. So limitation of this study is experimental design needs to be fine-tuned. So all of these runs and experiments was kind of preliminary experiment to more like understand the experiment. And more data analysis need to reach the conclusion. And obviously, we need more participants to have a generalized view and to reach a conclusion. So next step of our study will be further analysis on the data acquired from this experiment. So far, we have done only on experiment 1. So next we'll do for other designs too. So that we can find if there is any time effect, any presentation effect, any stimuli effect. We will design more experimental design to find the optimum design, like using different context, different color, sign, shape, auditory, or we'll use the auditory or haptic presentation. And different presentation system we will use, like we used already different kinds of, like 4 of them were kind of same and 5 was kind of different. And obviously it's a must requirement. We need much more participant. we will reject with more electrodes. Like in the topography, we have seen there might be something more in central parietal region. So maybe we will include those electrodes in our further study. Find out the brain region functioning while binary decision making. Obviously, that's our focus. Find out the brain region, that is electrode which emits classifiable signal. That is our another primary focus. That we not only want to understand the brain region, we want to use it to classify so that we can use the signal for to control the device or system. So that's all from me today. If you have any question, please.
Okay, thank you, Kazi.
Thank you, sir.
Any question from Kazi? Any question? Come on, guys.
I guess it's a little bit different from your sort of domain of expertise, but you know, it's pretty.
Why don't we start the question from you, Dr. Song,
Oh,
to
yeah.
warm up?
Oh, yeah. So, yeah, probably the audience is a little bit quieter today because it's a little bit different from their own expertise. But some of the things that I might ask you, Kazi, is how would you envision once you find the practicality of this, identifying the different brain regions associated with the motor vehicle, motor performance. How would you envision this in terms of applying to the actual uh, domain of control of autonomous system or semi-autonomous system?
So when I think of understanding the decision making, brain function of the decision making region, I want to understand or identify the brain region mostly because the challenges we find with traditional BCI, like the devices are heavy and the users are complaining about stress and fatigue about using this. But when we will be able to locate the exact location of the decision making, or in our case binary decision making, then maybe we will able to simplify those kind of steps. Like as you have seen the P300 speller matrix video, the lady is wearing lots of like kind of spider legs around her head. But if it is like just a clip or just a band in her head, then maybe it's more easy to use. And when we think about BCI, we normally think of people who are already physically challenged. So when they use those kind of heavy devices, it's more they like kind of get discouraged or demotivated to use that. But if we use that thing, that will be more beneficial. And another thing is we choose the binary decision making because binary choice, I think, is the building block of all those complex tasks. If I want to go to if I want to go to school, I will think when I will start. And if we want to simplify, we'll think from binary. We can think it from binary basis, like shall I start at 8 or shall I start at 9? Or shall I start at 9 or shall I start at 10? Then again, this node I shall use. So a complex task can be divided into a simpler building blocks. So that's what that's where I think it can be used.
Yeah, one of probably I have will ask another question, piggyback on the answers you have. One of the challenges that we have here is, as you talked about at the beginning of your presentation today, there are two kinds of things, temporal dimension as well as the spatial dimensions. Um, but when you look at the EEG equipment, it's not so great in terms of spatial, uh, dimension. And also, it's not even possible to identify the depth of the brain, how far you can go down for that. So it may not be even entirely feasible to pinpoint the location of the brain to, corresponding to the certain potential motor behavior. Do you have any insight on how you would compensate that challenges, and how would you utilize that in terms of interpreting your result?
Well, yeah, that's the challenge with EEG. Like one of the benefit of the EEG is like it uses lots of electrodes, and the more electrodes we will use, the more temporal data or temporal characteristics we will able to detect. But in our study, we already used few electrodes, and we also want to identify the brain region and the fewer electrodes as possible, maybe one electrode or maybe two electrode. Then that will be something kind of help with the BCI, because the spatial resolution, the techniques with good spatial resolution, those are not very friendly with BCI devices. But if we are able to do it with EEG, and if we are able to classify the signal or identify the signal from maybe not pinpoint, but if one or two electrode is we can do that, then that will be very helpful for the BCI.
I don't want to dominate the whole, question and answer session, but I want you to think about in terms of, I think you're mentioning like a one or two electrodes measuring to something that we need to get is a great thing. So if you can look up the idea of neuroplasticity, that'll be something that you can actually look into, how brain can react to the certain, you know, cognition at a minimal energy expenditure. So that's just my suggestion. Thank you.
Thank you.
Okay, any other question from Kazi? Okay. Then, at this point, maybe we should thank the Kazi for a great presentation. Thank you, and good luck.
Thank you, sir.
Bye-bye now. Bye-bye,
Thank you.
everyone.
Thank you, everyone.
Thank you, everyone.
Dr. Homer. Thank you, Dr. Homer.
Bye-bye. Bye-bye.